Okay, for chem bonding TBL set B questions. So the first question, which of the following ionic compounds is likely to show the greatest covalent character? So recall, extent of covalent character depends on two main factors. Number one, polarizing power of cation, which is directly related to the cation's charge density. So charge density is your charge over your radius, the size, and also the polarizability of anion, which is related to the anion size and charge. So if you take a look at all these ionic compounds, you have, of course, your barium 2+, Be 2+, Mg2+, and K+. Alright? K+ will automatically be out because it has a very low polarizing power. Okay, so D will be the obviously wrong answer. Now, between all of this, barium will be the next one I will cancel out. Why? Because barium is also very large. It's the last, it's down in group 2, alright? So it has a very large size. The polarizing power will not be large because of the large ionic size of barium. So now we're left with beryllium and magnesium, and since both of them have the same anion, F-, right, it makes sense for us to choose beryllium because beryllium has the most polarizing power. Okay, with that, therefore answer is B. We'll move on. Beryllium is diagonal to aluminum in the periodic table and it shares similar properties. Alright, which structure for the compounds of beryllium and fluorine are possible? So what's the purpose of telling you this question? So if you take a look at beryllium and fluorine, so typically you have this formula BeF2. Okay, you can see this beryllium itself, it's similar to aluminum in Al. Cl3 is electron deficient. And therefore it will try to accept electrons through dative bonds to achieve octet or more stable octet configuration. So from option 1, if you take a close look at this, the dative bond, can beryllium being electron deficient still dative bond to fluorine? That will not be correct, right? Because the arrow should be the other way, where fluorine dative bond to your beryllium. Right? That will make more sense because beryllium is already electron deficient. How can beryllium still dative bond to fluorine? Alright, so this option 1 is therefore wrong. The arrow should be pointing the other way. Alright? Okay, option 2, we focus on the beryllium. We do see the series of double dative bond being formed, and it's the correct direction now. And in this case, you can see this beryllium, this particular beryllium, has 4 bond pairs around it. It has achieved its octet configuration. So this is possible structure. Alright, because beryllium is now stable. The last but not least, this beryllium here also similarly accept 2 dative bonds from fluorine, 2-. Alright, so it also achieve an octet configuration. So that's also possible. And therefore, option 2 and 3 are possible answers. And therefore, answer C. Okay. So last one, because of 2-, you have 2 fluorine that becomes F- that can dative bond with beryllium. Okay, moving on to B3. Which of the following compounds does the first compound have a higher melting point than the second compound? So to look at boiling point, melting point, we must look at the structure and bonding. So this is just a tedious question. SiCl4 is a simple molecular structure. We are looking at IMF. In this case, it's non-polar, and therefore it has a weak intermolecular IdId. SiO2, on the other hand, will be giant molecular. When you are doing melting for giant molecular, we are breaking strong and extensive covalent bonds. So which one will be higher? Of course, the second one compound will have higher melting point than your first compound, and therefore it's not A. Okay, what about NaCl and N2O? NaCl and N2O both have giant ionic lattice structure. So in this case, you are breaking ionic bonds between opposite charge ions. The question is, which ionic bonds will be stronger? So recall, how do we compare ionic bond strength? We look at lattice energy. So Q plus Q minus over R plus plus R minus. The main difference is that we now have O2 minus versus Cl minus. Alright, so O2 minus versus Cl minus. So you can see that the charge on O2 minus is larger. So as a result, you do expect ionic bonds in Na2O to be stronger. Alright, it has a larger charge and a smaller radius than Cl minus. So you do have stronger ionic bonds between your opposite charge ions in Na2O. So as a result, the second compound in B will also have a higher boiling point or melting point than your first compound NaCl. Okay, moving on to C. NaCl, same giant ionic, so you have strong ionic bonds. There's nothing complicated about it. AlCl3, although you have a metal, non-metal, but we hope you remember it's an anomaly where it's a covalent compound due to the high polarizing power of Al3 plus and the high polarizability of Cl minus, and this induces significant covalent character, and therefore AlCl3 is a simple molecular structure with no net dipole, and therefore it's a weak intermolecular PDBD. So in this case, this is the only option in which where your first compound has a higher boiling point, melting point than your second compound. Okay, for the last two, both of them are organic molecules, so they are simple molecular structure. Okay, so for the second compound, you have OH bond, which means you have intermolecular hydrogen bonding. Whereas in this case, although you have O and H, but the O and H are not bonded together, so instead of having hydrogen bonding, you only have your PD-PD because you have a dipole moment along your O and your C. Alright, that's all you have. You don't have hydrogen bond. So in general, hydrogen bonds are stronger than PD-PD given that they have comparable molecular MR. So D, the second compound, will have a higher boiling point, melting point as compared to D. Therefore, in all the options, only C fulfills the correct option. Okay, if not, we'll move on to B4. In B4, in a single covalent bond, one pair of electrons shared by two atoms, which statement is true for all single covalent bonds. So what this statement is trying to say is that in a bond between A and B, I have a dot and a cross, a shared pair of electrons. So covalent bonds are formed when bonding electrons are shared equally between two atoms. Is this true for all single covalent bonds? So you do remember, right, we do have delta plus, delta minus. So when I write delta plus, delta minus, what does it mean? It means that these electrons are closer to B than A. So is it that electrons are shared equally? It's only shared equally when you have non-polar covalent bonds. Alright? Where for polar covalent bonds, involve unequal sharing of bonding electrons. So therefore option A is not true all the time. Option A is incorrect. Covalent bonds allow the atoms involved to complete the valence shell configuration. Is that always true? That's not true. Why? Because, example, molecules like BF3, right? We discussed this earlier on. So AlCl3, BF3, AlCl3. You do have centers or atoms which are electron deficient. We also have examples in which you have expanded octet. So it doesn't necessarily always lead to completing valence shell configuration. Alright? Option C, covalent bonds formed between atoms of different electron negativity are stronger. This may be somewhat true. We do observe certain trends, but do note that there are multiple factors that affect the strength of covalent bond. For example, the extent of orbital overlap is one key factor that affects the bond strength. So example, HH bond, because the extent of orbital overlap it's much higher because the size of the atoms of H is small. Although HH bond is non-polar, alright, HCl bond is polar, of course. You can see the bond energy of HH bond is somewhat slightly stronger than the HCl bond. Alright, so it is not just the only factor that affects covalent bond strength. Polar bonds, we do observe a general trend that polar bonds are stronger, but it's not true for all time, and therefore option C is not a good option. We will ignore it, and therefore we look at option D. The formation of covalent bonds always involve the formation of sigma bond. So you remember, as every single bond formed is always a sigma bond, followed by a pi bond. So sigma bonds are always formed first before pi bonds are formed. So for single covalent bonds, sigma bonds are always formed. So therefore option D is correct, and therefore answer D is the answer for B4. Okay, for the last question, B5, this is the most painful question of the lot. We have to determine one polar and one non-polar molecule. So you have a series of compounds. The whole idea is that we need to consider the dot and cross, consider the shape using VSEPR before we can consider the polarity. So I know that it's going to take a long time. My suggestion is for you to pause the video, try to draw the dot and cross, try to determine the shape, and therefore the polarity. Alright, I'm going to teach you a shortcut after this. So for AlCl3, a shortcut will be Al has 3 valence electrons, right? Then you have surrounded by 3 chlorine. So you will form single bond with Cl. Cl has achieved octet, but aluminum has no more valence electrons, so it's perfectly fine. You have 3 bond pairs and 0 lone pairs around aluminum. It will be trigonal planar, it will be non-polar, Alright, because as the dipole moment cancel each other out. Whereas for Al2Cl6 is basically a dimer, so you can draw this. Around the Al is tetrahedral, because you have 4 bond pairs, 1, 2, 3, 4. 4 bond pairs around the Al atom, 0 lone pairs, 2 tetrahedral, and the dipole moment cancels out, and therefore it's non-polar. So A will not be the option, because both of them are non-polar. How about POCl3 and PCl3 then? POCl3, P, central atom, it will form a double bond with O. Okay, so this is a trick I'm teaching you. O will require a double bond. Then for the remaining 3 Cls, you will form a single bond each. So you end up with a system of 1, 2, 3, 4. 4 bond pairs. So how do I know this dot and cross this structure is correct? Because if you were to count the number of valence electrons contributed by phosphorus will have 5 valence electrons. Right? So cross, cross, dot, dot, cross, dot, cross, dot, cross, dot. So I've counted for 5 crosses over here already. Your phosphorus has used up all the electrons, valence electrons. And in this case, it's perfectly fine for phosphorus to expand octet, because phosphorus, although it has 10 electrons on it, it's perfectly fine because phosphorus can expand octet due to its available 3D orbitals, alright, to expand octet. So you do have 4 bond pairs, 0 lone pairs around phosphorus atom. It's tetrahedral, but although it's tetrahedral, it's polar because PO bond is more polar than PCl bond because O is more electronegative than Cl. So the dipole moments don't exactly cancel out. Okay, for PCl3, it's going to be trigonal pyramidal, so it's going to be polar. Dipole moments do not cancel each other out. So it's a very classic example. You can just think of NH3 as a parallel. Okay. Second last option, we have O as central atom. So this mirrors like H, O, H, right? Why? Because Br also form a single bond. So you do expect H, Br to be bonded to O, and then bonded to H. And then you will see that O oxygen, just like water, has 2 lone pairs, 2 bond pairs, 2 lone pairs, you have band. So it definitely be polar. Alright? So the dipole moments cannot cancel each other out. Similarly for OBr2. Alright, so its band is definitely polar. So in this case, both option B and C involve 2 sets of both polar molecules. They will not be the correct answer. And then we're left with now potentially only option D, which to me is surprising because XeF2 and XeF6, when some of you see XeF6, you may think immediately that it's octahedral and therefore it cannot be polar. Okay, so for XeF2, Xe, recall, has 8 valence electrons. Okay. So Xe is central atom surrounded by 2 fluorine. So you have used up 2 electrons for the covalent bond, which means you have 6 more electrons to assign as lone pairs. So you end up with a 2-3 system, 2 bond pairs, 3 lone pairs. And this corresponds to a linear shape, and therefore it's going to be non-polar because the dipole moment can directly cancel each other out. Okay, so non-polar. But what about XeF6 then? So remember, Xe has 8 valence electrons. Now you're surrounded by 6 fluorine atoms. You use up 6 electrons for covalent bonding. So over here, 1, 2, 3, 4, 5, 6. You have a lone pair. So what do you realize about lone pair? Lone pair, when you have lone pair, to minimize repulsion, the shape will not allow for something that allows dipole moments to be cancelled out. So this shape happens to be what we call pentagonal pyramidal. It's the first time you will see a total of 7 electron pairs, 6 bond pairs, 1 lone pair. So lone pair takes on the acyl position, just like what we do for trigonal pyramidal. Alright, octahedral structure. Alright, we put a lone pair at the bottom, and the rest of it orientate it to minimize repulsion. So you have a polar molecule in which you have a net dipole, and the dipole moments do not cancel out. Alright, so in this case, D will be the option because you have a non-polar and a polar molecule.